All right, and now it is time for the third speaker in this session. So, Yuxing Dong, come on up. Let's get the slides. Yes. Should be here. All right, and so we have contrastive learning with frequency domain interest trends. Thank you.
Ladies and gentlemen, distinguished professors and fellow peers, good afternoon. I'm Dong Yuxin from Harbin Engineering University, and it's really an honor for me to share our thoughts on contrastive learning with frequency domain interest trends for sequential recommendation. There are two challenges and innovations for our thoughts. The motivation, the first is the sparsity and noisy interaction limit the model's ability to understand users' intention. The second is the complexity of time series and the low frequency preference limit the utility of sequence encoders. For example, constructing augmented symbols in the time domain poses challenges to various reasons, such as fast evolving trends, interest shifts, and system factors. The solution for challenge one, we propose a contrastive self-supervised learning model aiming to learn a high-quality encoder by maximizing the consistency of the positive symbol pairs and pushing the negative symbol pairs apart. And for solution for challenge two, we expect to construct self-supervised symbols from a frequency domain perspective. As shown in figure 1a, and improving the ability to discriminate between events of different frequency sizes. As you know, most previous approaches just ignore the effect of the trend of hidden dimensional features on the user interest pattern, as shown in figure 1b. The interest trend referred to the difference between a certain feature attribute in the hidden place and its surrounding value, indicating the user's attribute inclination at a particular moment. As shown in figure 2, we observe that the low frequency components just represent the smooth trend. In contrast, the third one, the high frequency components represent the areas of dramatic change, just indicating the degree of the change tendency of each pixel. In light of this, we propose a novel data augmentation strategy with interesting trends, which control the frequency size of spatial temporal frequency domain representation via mask filtering. Okay. So there are our contributions. The first is, to the best of our knowledge, is the first time that a spatial temporal frequency domain approach has been applied to construct self-supervised signals based on interest trends for the sequential recommendations. And also, we propose a multi-task learning solution which combines recommendation tasks and contrastive learning tasks to learn high-quality user representation. And here are the architecture of our model. We show the overall architecture of the proposed model. And combined with the two kinds of tasks in this paper, we designed 3 data argumentations, including low pass, high pass, and band stop argumentation to construct high quality self-supervised signals. And this is the 2 kinds of learning method. Following the state-of-the-art model such as DUREC and CL4S-REC, we employ a transformer to encode the sequence recommendation, as you know. Transformer is very popular. It's a powerful method for encoding sequences based on self-attention mechanism and has achieved promising results. And firstly, the sequential recommendation can be treated as a classification task for the whole atom set, which predicts the likelihood of the next atom. Given the user representation H and atom embedding matrix E, the score of the next atom is calculated as shown below. Here, let's introduce the contrastive learning. The complexity of time series and low frequency preference just limit the utility of sequence encoders. To address this issue, we construct samples of different frequency sizes. The data argumentation operators, we have introduced 3 data categories: low pass, high pass, and band stop. LPA just adopts the low frequency components as argumented samples, which represent the slowly evolving trend of the attributes. And HPA treats the high frequency component as argumented samples, which represents the rapidly shifting trend in attributes and corresponding to the path away from the center. And the BSA, which stands for band stop argumentation, randomly suppresses a certain frequency component and takes the rest as argumented samples. For constructive loss, to improve the encoder discrimination, constructive learning maximizes the agreements between positive pairs from the same instance. We require a constructive loss function that minimizes the difference between 2 argumented samples from the same sequence and maximizes the difference between 2 argumented samples from different sequences. Okay? Finally, we expect the user's representation encoder to accommodate different frequency components and thus improve the inference power. We simply linearly weight the above losses to obtain the final constructive loss as follows. Both recommendation learning and constructive learning optimize the user representation encoder, which models atoms within sequences. Consequently, we adopt a multitask learning framework to calculate the total constructive loss in a linearly weighted way as follows. Next, let's introduce the experiment part. We just conduct extensive experiments on 4 publicly available data sets to investigate the following questions that we consider, which are the beauty, clothing, sports, and ML1M. The first question, the research question we consider is, how does the proposed model perform compared to the state-of-the-art baselines? Second one, how do different data argumentation operations impact the performance of the model? Third one, does the proposed model perform robustly against the data sparsity and noisy interactions. Fourth one, how do different hyperparameter settings affect the performance of the proposed model? So, to evaluate the model preference, we designed the evaluation metrics, which are hit rate and NDCG. And the competing models are just as the following. And for the first, the results of the first experiment shows significant improvements over the state-of-the-art models on all data sets. In particular, our model achieved a 12.75% to 24.75% improvement in HR and NDCG compared to the strongest baseline on ML1M. Such results just demonstrate the superiority of our solution. We attribute such improvement to the proposed data augmentation operations and then stop, which make the user representation encoder accommodate different frequency components. That's what we want. The second experiment result we observe, we just designed multiple variants for ablation experiments. We use 2 default models and indicating the proposed one with the 3 augmentation operations. What we observe, first, the model with contrastive learning consistently outperforms on all data sets, which confirms the effectiveness of contrastive learning. The second one, different data sets just focus on different frequency components. Third one, we suspect that the frequency components emphasized by the model depend on the data set's configuration, such as sparsity and the speed of interest evolution. Last one, we observe that the additional BSA can further improve the performance in most cases, which demonstrate the effectiveness of the BSA. The third one, to simulate data sparsity scenarios, we keep the test data set unchanged and only tune the percentage of the training data set. After the comparison, we observe that the proposed model consistently outperforms dual-rec on all data sets. To evaluate the effect of noise interactions on the model, we train the model on the original training data set and randomly replace a certain percentage. Significantly, keeping the maximum sequence length, we observe our proposed model consistently outperforms dual-rec on all data sets, which demonstrate the superiority of our solution again. Last experiment, we try to make research on the influence of different important hyperparameters in our model studies. The performance drops sharply when SCAM increases to a certain threshold, which means that it will degrade the efficiency of sequential recommendation when constructive learning dominates the learning process. Second one, a smaller appropriate dropout can improve the performance. In contrast, a drop-off over a certain threshold range leads to a sharp degradation in performance. So, we suspect that a larger drop-off causes an intrinsic change to the frequency of the original sequence. And also, we observe that either too large or too small thresholds limit the quality of the desired frequency domain components. The threshold range varies for different data sets. Such results suggest that the bounds of low and high frequencies needs to be fine-tuned to achieve a better performance. The further analysis shows that we observe that more high and low frequencies achieve better performance. And we observe that the filtered data with a suitable threshold realize a performance close to or even exceeding the original data in most cases. So this may indicate that the filtered data can be utilized as self-supervised sample for training. That's all the experimental results. Last, let me show you the conclusion of our work. First, we propose a novel contrastive learning method with frequency domain interest trends for sequential recommendation. Second, we introduce second-order frequency domain representations to construct positive samples for constructive learning, which allows the sequence encoder to accommodate different frequency components and improve its inference ability. Third one, the components of different frequency sizes reflect the interest trends between attributes and their surroundings in the hidden place. Thus, we can strengthen the ability to discriminate features with different degrees of interest trends. Extensive experiments results on the full public benchmark data sets show that our proposed model achieves significant improvements and outperforms the state-of-the-art baselines. Our future work, we should consider how do we design learnable argumentation models. Moreover, we can further study how to add supervised information to construct high-quality augmented samples. And that's all I want to present. Thanks a lot. This is my contact, and welcome to our university. Thank you. If you have any questions.
All right, let's thank the speaker. Do we have questions from the audience? We have a question here.
Hi, thanks for your great presentation. My question is, what's the main difference of your data set for different components? Thanks.
Okay. Thank you for your question. Our experimental results just make comparisons with different frequency sets, the influence for different atoms. Let me show you. Different data augmentation operations we can observe. Here is an example, maybe can explain the effective and the results of our model. For example, you can see from the picture in the clothing and the sports refer to high frequency component. And beauty and ML1M dataset concentrates more on the low frequency components. So that's just mean different data sets focus on different frequency components. So although there is a threshold, this we can have a good indication to explain the results. Thank you.
Okay, thank you.
So I had a question about the, you have this, you have the high frequency and the low frequency cutoffs, and then there's the band stop one kind of in the middle. That's chosen as a random component. I'm wondering if there is kind of a more principled way to choose the, instead of picking a random component, should you pick something that's in between the other two? I mean, yeah, I'm just wondering if there's a strategy that could be used there.
Yeah, thank you. The reason why we use a combined method for low and high frequency, we know that there is a disadvantage for the sparsity and noisy interaction, and also as well as the complexity of time series. So the question, you asked the question very good. Good question. Because the third one, we use band stop argumentation, and we want to hide some pixels, right?
Right.
So the strategy we use just is randomly choose. And results show that if we use transformer method, the learning ability is very strong. And now, at present, the strategy is just randomly chosen. Maybe in the future, we will try to find a combined, maybe 2 or more pixels hidden. Here is just randomly choose 1 pixel chosen.
Right.
And we represent the information in each pixel. We use them as the user's preference, interest information. We put the information into the pixel.
Right.
So it's a good, I think it's a good choice for us. Thank you.
Any other questions? I think we are out of time, so let's thank the speaker again. Thank you.